Assalamualaikum warahmatullahi wabarakatuh, and a very good day to all the panels. We are from Group 1, consists of me, Muhammad Ini, Ahri Shankaran, Ambu Karasi, Muhammad Nur Faiz, and Wan Aidit. And our plant design title is the production of 100,000 pound per hour methanol plant. First and foremost, I would like to start my group presentation with the first part, which is process improvement. So this is our PFD before we do our correction. For process improvement, there were 3 corrections that we have done based on the comment given. The first one is the root selection explanation. The second one is carbon monoxide accumulation, and the third one is energy balance manual versus the simulation. For process root selection, CO2 to methanol reaction is inherently more selective and result in fewer byproducts. The reaction conditions are milder due to less exothermic reaction, which in turn result in safer operation, better carbon utilization compared with conventional syngas. CO2 recycling will ultimately be beneficial for the global of CO2 emission. CO2 and H2 are added in separate pure stream and independent of each other, depending on the catalyst requirement, may be adjusted precisely without the need for expensive reforming equipment. The conversion of carbon dioxide to methanol is 29.2% in carbon dioxide hydrogenation. This conversion rate can be achieved when the raw material consumed are purified and has high purity. Thus, methanol production from syngas or thermal decomposition doesn't promise a high conversion of methanol due to purity of reactant produced from reforming or thermal decomposition. So the second one is carbon monoxide accumulation. So this is the PFD after we have considered the correction given by the panels. We will quickly talk about the carbon monoxide waste management. Carbon monoxide waste need to be treated in systematic way so that it can be useful and not harmful to the surrounding. Small percentage in the stream contain carbon monoxide, carbon dioxide and hydrogen gas. The stream will go through a catalytic converter to convert the carbon monoxide into carbon dioxide. Then we will separate the hydrogen and those carbon dioxide and store them.
This table shows the comparison between the manual energy balance calculation and the simulation from the Aspen. All of the percentage error are below 15% except for stream 1. This is because stream 1 should not have any enthalpy given that hydrogen did not have heat of formation.
Heat integration. Pinch technology analysis is to be applied for the heat integration of the production plant. Out of the various methods to conduct pinch analysis, the problem table algorithm method was chosen to conduct the analysis. First, data such as target and supply temperature and heating and cooling requirement in kilowatt is obtained. This table shows the actual value for heating and cooling stream. The heating requirement is 36,874.79 kilowatt and the cooling requirement is 337,533.99 kilowatt. Next, supply temperature and target temperature are shifted according to delta T minimum, which is in most cases are 10 degrees Celsius. 10 degrees Celsius is a typical range of delta T minimum for chemical plant. This table shows the shifted values which is only for hot streams. The shifted temperatures are set up in intervals and similar values are removed. This is done in temperature interval heat balance to obtain the interval value of Q. Problem table algorithm is used to determine heat change as basis for heat table cascade. Heat table cascade is used to determine the minimum heating requirement, minimum cooling requirement and the pinch point. From this table cascade, we obtained 424 degrees Celsius as T pinch cold and 434 as T pinch hot. Meanwhile, The QH minimum is 0 kilowatt and QC minimum is 301,430.3 kilowatt. Followed by that, stream pairing is done using maximum energy recovery method. There are several rules of thumb to conduct this method, where for region above pinch, heat exchange could only occur if cold capacity is more than hot capacity. For region below pinch, heat exchange could only occur if hot capacity is more than cold capacity. Since the supply target temperature of all streams are below T pinch hot and T pinch cold, therefore heat exchange matching can only be done for below pinch temperature. Therefore, the first match is done between H1 and C2, since H1 has the higher FCP than C2. Followed by that, another matching is done between H1 and C1 because H1 has enough heat to transfer to C1, which is 771.0682 kilowatt, while the remaining hot streams and H1 as well are cooled using external cooler to achieve desired temperature. Besides, it is also ensured that the temperature of streams after matching do not violate delta T minimum, which is equal to 10 degrees Celsius. Moreover, the diagram is justified with recalculation of QH minimum and QC minimum. Based on the calculation, it is proven that QH minimum equals to 0 kilowatt and QC minimum equals to 301,430.3 kilowatt. Finally, the utility saved is calculated. The energy saved for heating process requirement is 100%, while for cooling process is 10.7% of energy is saved. Finally, this is the flowsheet modification after the hand design, which is drawn by referring to grid diagram. Thus, it is proof that energy is saved through this heat integration. Process optimization. In this design, the optimization was conducted on distillation column DC01. DC01 is the last separation unit which is responsible to produce methanol of set purity as distillate. In order to solve the distillation column, is optimized by minimizing reflux ratio. In our design, the main product methanol with a purity of 99% will be leaving DC01 as distillate product. Thus, the optimized design of this distillation column will ensure the production of methanol with the least utility and capital cost. In this sense, the optimization on DC01 will be done by manipulating the pressure of the column. The decision variable, the objective function and the constraints are stated as well. From the optimization, we have obtained the lower reflux ratio is 0.83 at 2.5 atm, but the capital cost and operating cost remained constant even though the reflux ratio decreased. The total utility reduced significantly at 2 atm but increased slightly for 2.5 atm even though the capital and operating cost remained constant. Thus, the optimum pressure and the reflux ratio value obtained is 2 atm and 0.93 respectively, which design the distillation column in an economic and energy efficient way. This is the summary for capital cost, operating cost, heating utility, cooling utility, and total utility of before and after optimization. By assuming 20 years of lifetime for the equipment, annualized capital cost is determined by dividing the capital cost by 20 years. Annualized total cost is determined by adding up annualized capital and operating cost. From the previous summary of cost and utility, as the reboiler and condenser utility reduces, the operating cost reduces. From the optimization, the reboiler utility at 2 atm increases by 2582.9 kilowatt, but the condenser utility reduces significantly by 27,972.8 kilowatt. This makes the total utility to be saved by 32.54%. However, the cost is saved by only 3.24%, which is less than 5% because of the operating cost. This is caused by the low difference between the operating cost of before and after optimization. In most distillation column, the major operating cost is reboiler energy consumption, which makes the reduction in operating cost insignificant. Thus, the total annualized cost before and after is saved around 3.24% only.
So So the next one is equipment sizing and mechanical design. So this is methanol production plant equipment list. Total major process and auxiliary equipment in the methanol plant. The equipment and the equipment ID number are listed.
The first is the equipment specification for reactor R01. The type of reactor is packed bed reactor and the function is to produce methanol through the reaction between carbon dioxide and hydrogen. The process specification details as stated in the slide. This is the equipment properties for reactor R01. The type of the reactor R01 is vertical and the material of construction is stainless steel 316 and the other equipment properties are as stated.
This is the mechanical design of the methanol synthesis reactor. It is a vertical fixed bed reactor made of stainless steel.
This is the equipment specification, function and process specification for distillation tower DC01. The function is to separate between methanol and water, and the process specification are as listed. This is the equipment properties of distillation tower DC01. The type of distillation tower that we use is vertical, and the material of construction for this distillation tower is from carbon steel, and the other equipment properties are as listed. This slide is about equipment specification sheet, process specification of the condenser. The heat duty Q for condenser is as stated in this table. There is two streams, which is hot and cold medium. The inlet temperature for hot is 74.9 degrees Celsius and outlet temperature is 74.4, and for cold medium the temperature is 30 degrees Celsius and the second one is 35 degrees Celsius. This slide is about equipment properties of condenser. The type of condenser is fixed head cross flow heat exchanger and the material construction is carbon steel, and the other equipment properties is as stated in the table. So the next slide is about equipment specification sheet and also operating condition for a reboiler. The heat duty Q for this reboiler is as stated in this table, and there is two stream inlet and outlet for hot and cold medium. For hot, the inlet is 175 degrees Celsius and outlet is 174. For the cold, the inlet is 133.3 degrees Celsius and outlet is 133.8 degrees Celsius. This is about equipment properties of a reboiler. The type of reboiler is fixed head cross flow heat exchanger and the material construction is carbon steel. And also the other equipment properties for reboiler is as stated in this table.
This is the mechanical design of the reboiler, which is a fixed head cross-flow heat exchanger. The material of construction is of carbon steel.
So the next equipment is about flash drum FD01. The function of it is to separate carbon monoxide, carbon dioxide and hydrogen from water and methanol. The process specification are as listed in the table. Same goes to flash drum. The material that we use is carbon steel and the type of the equipment is vertical. The other properties of equipment are as listed in the table.
This is the mechanical design of flash drum FD01. It is a vertical type of flash drum. Material of construction carbon steel.
This is the equipment specification for flash drum FD02. The function is same as flash drum FD01, which is to separate carbon monoxide, carbon dioxide, and hydrogen from water and methanol mixture. And the process specification of flash drum FD02 details are as stated. The equipment properties for flash drum FD02 is also similar to flash drum FD01, except for their sizing, which is different in terms of their vessel internal diameter and vessel height. Next is the equipment specification sheet for compressor PC01, and the function of PC01 is to compress raw feed material pressure, which is stream 3 from 1 atm to 29.91 atm, and the brake horsepower of the compressor that we get from the Aspen simulation is 369,648.72 horsepower, and the other details as stated in the slides. This is the equipment properties for compressor PC01. The type of the compressor is 3-stage steam turbine driver, which is suitable for high operating pressure, and the material of the construction is stainless steel. This is the equipment specification for mixer M01, and the function of M01 is to mix stream 1 to 11 and 15 before entering pressure compressor PC01, and the volumetric flow rate of mixer M01 is 86116.67 feet cube per hour, and the other process specification as stated. This is the equipment properties for mixer M01, which the type will be in vertical, and the material construction is carbon steel, and the other details such as weight as stated in the slide, which is important in determining the costing of this equipment. In our plant, we got two heat exchangers. The first is heat exchanger E01. The function of E01 is to provide heating to cold stream C2, and the other process specification details are as stated in this slide. This is equipment properties for heat exchanger E01. Type of this heat exchanger is floating head cross-flow heat exchanger, which is suitable for exchange heat between two gases. And the material construction for this heat exchanger is carbon steel, and the other details are as stated in this slide. This is the equipment specification for heat exchanger E02, and the function is to provide heating to cold stream C1, and the other details as stated in this slide. This is the equipment properties for heat exchanger E02. Since the heat transfer area of E02 is less than 200 feet square, the type of E02 is double pipe heat exchanger, and the material construction is carbon steel. In this plant, we got 6 cooler, which is also function as heat exchanger. The first is cooler 1, and its function is to provide cooling to hot stream H2 from 412.23 degrees C to 400 degrees C, and the process specification as stated. The equipment properties for cooler C01. The type is floating head cross-flow heat exchanger, and the material construction is also carbon steel. For cooler C2, the function is to provide cooling to hot stream H2 from 400 degrees C to 250 degrees C, and the process specification are mentioned in this slide. This is the equipment properties for cooler C02. The type is also same to cooler C01, which is carbon steel, floating head cross-flow heat exchanger, and the difference is the heat transfer area. The function of cooler C03 is to provide cooling to hot stream H3 from 250 degrees C to 120 degrees C, and the process specification also can be seen here. And for equipment properties for cooler C03 also same to the previous cooler type, which is floating head, cross-flow heat exchanger, material construction of carbon steel. The function of cooler C04 is to provide heat cooling to hot stream H4 from 120 degrees C to 10 degrees C before entering the flash drum FD01, and the process specification also can be seen here. The type for cooler C04 is also floating head cross-flow heat exchanger, and it contains one shell with 8 tube passes, and the material construction is also same, which is carbon steel. For cooler C05, the function is to provide cooling to hot stream H5 from 63 degrees C to 25 degrees C. And the type for cooler C05 is floating head cross-flow heat exchanger with one shell and 4 tube passes, and the material construction for this cooler is also carbon steel. And the last is cooler C06. The function is to provide cooling to hot stream H6 from 100.67 degrees C to 25 degrees C, and the process specification also can be seen here. Also same to the previous cooler, for cooler 6 the type is also floating head cross-flow heat exchanger with one shell, 4 tube passes, and the material construction for C06 is also carbon steel.
So the next slide is equipment costing. This is the current chemical engineering CE index value. The base cost index is 567 and the present cost index is 603.1. This will be used to estimate the purchase cost.
The first is costing for reactor R01. Cost for vessel and platform have been included in determining the costing for reactor R01, and the FOB total purchase cost for reactor R01 is $764,323.19.
This is the cost for tower and tray for distillation tower DC01. After we calculate, the FOB total purchase cost of distillation tower DC01 is $306,922.84. This slide consists of costs for vessel and packing of a condenser. The bare module cost of it is $134,297.79. So the next one is about cost for vessel and packing of a reboiler. The bare module cost of it is $57,440.99. For the cost of the flash drum, the total purchase cost FOB for flash drum FD01 is $223,699.75. This slide is about flash drum FD02 cost for tower. FOB total purchase cost for flash drum FD02 is $153,513.83.
Next is compressor PC01. The bare module cost is $115,623,993.2. The cost is high due to the high volumetric flow rate of gas to be compressed and also high discharge pressure, which is 30 bar, which require a high power of compressor to be used to compress our stream. For mixer M01, after including total purchase cost, platform and ladder cost, the bare module cost for mixer M01 is $9,406,616.16. Moving into our heat exchanger, for heat exchanger E01, the bare module cost is $126,666.50. And for heat exchanger E02, the bare module cost is $60,889.13. For cooler costing, there are 6 coolers in our plant, and the first is cooler C01. The bare module cost for cooler C01 is 161,337.36. For cooler C02, the bare module cost is 284,379.54 dollars. And for cooler C03, the bare module cost is 268,400.30 dollars. Next is bare module cost for cooler C04, which is 555,335.38 dollars. And for cooler C05, the bare module cost is 101,054.25 dollars. And the last is cooler C06, which the bare module cost for cooler C06 is 75,431.14 dollars.
In this slide, we can see the equipment listed for this methanol synthesis plant and also the bare module cost of each equipment and also the total bare module cost for the total equipment. For the estimation of total capital investment, preliminary estimate method is used as it provides the most accurate value. This method is the best carried out after an optimal process design has been developed, complete with mass and energy balance, equipment sizing, selection of material of construction, and also development of a process control configuration as incorporated into a P&ID. After we calculate the total bare module cost CTBM, we have calculated the total permanent investment CTPI and also the working capital CWC, and the summation of these three values, we will get the total capital investment CTPI, which is 252,326,050.7 dollars.
Process control. The reactor R01 reactor is an isothermal reactor. The reactor is designed with a jacket for cooling utility flow. Any fluctuations in the reactor temperature might give unwanted consequences such as changes in conversion rate, which would alter product quality, reactor wall disintegration, or even explosion. Thus, temperature is an important parameter to be controlled. Other than that, pressure, which would cause similar consequences, should be controlled as well. Furthermore, flow into the reactor should also be controlled in order to attain desired production. To control the temperature inside the reactor, the temperature in the reactor is measured and the flow rate of cooling utility into the reactor is manipulated. The control configuration is cascade control because temperature of cooling utility and reactor are cascaded to control the temperature inside the reactor. To control the pressure inside the reactor, the pressure inside the reactor is measured and the outlet flow rate from the reactor is manipulated. Thus, the control configuration is feedback control. Furthermore, the flow into the reactor is controlled to prevent the overflow, which will cause pressure buildup. Thus, the flow rate of mixture into the reactor is measured and manipulated. The control configuration is also feedback control. Next, for flash drum, the pressure, level of the flash drum, and flow into the flash drums are controlled to maintain the efficiency of separation. The level in the flash drum is controlled by measuring the level of mixture in the flash drum and manipulating the flow rate of outer liquid stream at the bottom to make sure the mixture level is maintained to prevent from overflowing, which will affect the separation process. To control the flow into the flash drum, the flow rate of stream inlet to the flash drum is measured and manipulated to prevent overflow into the flash drum, which will cause pressure buildup and overflooding. Furthermore, the pressure in the flash drum is controlled by measuring the pressure inside the flash drum and manipulating the vapor stream that exits the flash drum to prevent accidents like explosion, as well as to maintain the separation of the component. The control configuration for all the control objective is feedback control because system output is measured and the input is manipulated to drive the process variable towards the desired point. Flash drum 2 has the same control configuration as flash drum 1 except for pressure. Flash drum 2 differs from flash drum 1 in terms of pressure because flash drum 2 has a pressure of 1 atm, meanwhile flash drum 1 has a set point of 4 atm. Thus, the control system for flash drum 2 must be set to reach the desired set point of 1 atm. The objective of distillation column control is to maintain the specified composition of the top or bottom product and to alarm any of potential serious hazardous deviation in the process condition. Besides, the distillation column control is also designed to prevent offsets in operating conditions such as pressure and temperature of the separation unit. The pressure of the distillation column is controlled by manipulating the flow rate of the stream that leaves the top of the column to achieve high separation efficiency, obtain high purity product and avoid pressure buildup in the column leading to explosion. The temperature is controlled by manipulating the flow rate of steam into reboiler and flow rate of cooling water into condenser to achieve desired separation efficiency and outlet purities and avoid extreme temperatures which may lead to pressure buildup and vessel rupture. Followed by that, the level in the distillation column is controlled to prevent flooding or overflowing of the column and to obtain the desired or pure product by manipulating the flow rate of the bottom flow. Apart from controlling the level in the distillation column, the level in the reflux drum is also must be controlled to prevent overflow, to avoid reflux dryout and to maintain product purity. The composition of distillate from DC01 should be controlled to make sure the product produced is of high purity, which is 99%, and it is done by manipulating the flow rate of reflux flow into the distillation column. The control configuration that is suitable for all the control objective mentioned is feedback control because the action is taken based on the measured variable and flow rates are manipulated accordingly to achieve the desired set point. Furthermore, it is important to control the vapor composition of the outlet stream from reboiler and enters distillation column. The flow rate and temperature of the stream re-enter the bottom of the column from reboiler might fluctuate. Correct amount of heating should be done to boil all the liquid that enters reboiler. A fully vaporized stream should be recycled into the column for better separation. Apart from bottom flow rate, the flow rate and temperature of top outlet from the distillation column might fluctuate as well. Correct amount of cooling should be done to condense all the vapor that enters condenser. A fully condensed steam must be recycled into the column as reflux for better separation. The suitable control configuration for both is feed-forward cascade control because it measures important disturbance variable and take corrective actions, and two process variables are controlled by cascading two controller, which is flow and temperature. The control objective of control system at the heat exchanger is to keep the exit stream's temperature at the desired value by varying the flow rate of cooling utility. Here we apply cascade control, which consists of primary controller, which is used to maintain the outlet temperature at desired value, and secondary controller, which is used to compensate for changes in the flow rate of inlet stream. All the heat exchangers has the same objective and control configuration except for justification. For cooler 1, the temperature of the outlet stream must control before flowing to next cooler C02 before reducing the temperature to the desired temperature. For cooler 2, exceeding or lowering the set point temperature would affect the conversion and reaction rate. For cooler 3, to reduce the temperature before entering the next cooler, which is cooler 04. For cooler 4, to reduce the temperature before entering flash drum 1 to be maintained as the mixture must be partially condensed to become a mixture of liquid and vapor to flash it out. For cooler 5, the temperature of cooler 5 outlet stream must be controlled at a set point of 25 degrees Celsius in order to be directed to the storage tank. For cooler 6, the temperature must be controlled in order to direct it to the wastewater treatment plant at 25 degrees Celsius. Control objective for all the valves in this design is to control the pressure to prevent the discharge pressure from exceeding an upper limit or being below the lower limit. Feedback control is suitable because the pressure output is measured and the action is taken by manipulating the valve. For valve 1, the pressure is at 4 atm to partially vaporize the mixture before entering flash drum 1. For valve 2, the pressure is set at 1 atm to partially vaporize the mixture before entering flash drum 2. For valve 3 is controlled to reduce the pressure of product to atmospheric pressure to be sent to the storage tank. Valve 4 is controlled to reduce the pressure of bottom flow rate to atmospheric pressure to be sent to the wastewater treatment storage. For a mixer, the parameters that are controlled are temperature, pressure, and flow into the mixer. The temperature in the mixer is controlled by using a feedback control by measuring the temperature in the mixer and manipulating the flow rate of steam into the mixer heat exchange coil and flow rate of cooling water into the mixer heat exchange coil. Next, the pressure in the mixer is controlled using feedback control by measuring the pressure of the mixer and manipulating the outlet stream from the mixer. Furthermore, the flow into the mixer is controlled by using the feedback cascade control because the flow rate of both recycle stream 11 and 15 is measured and manipulated. The control system for a compressor is introduced to prevent the discharge pressure from exceeding an upper limit or being below the lower limit. Feedback controller is sufficient in controlling the pressure because the pressure of the outlet stream from a compressor is measured, and according to that, the flow rate of the stream is manipulated to get the desired point, which is 29.61 atm. Overall piping and instrumentation diagram for a methanol production plant.
The next chapter is waste treatment. Waste treatment is very crucial in a plant to ensure that the plant follow the guidelines prepared by the Department of the Environment to ensure that the pollution to environment is kept at minimum. The wastewater generated in our plant is come from stream 23, which contain mainly water and methanol, and the temperature and pressure from this stream have been reduced to the standard operating temperature and pressure, which is 25 degrees C and 1 atm. The other waste generated in our plant is the accumulation of carbon dioxide, carbon monoxide, and hydrogen gas in stream 11. Carbon monoxide and hydrogen gas cannot be pushed into the environment since they have their toxic and combustible properties. And the below is the treatment of carbon monoxide and hydrogen gas flow process. It will go to the push stream, and this carbon monoxide, carbon dioxide, and hydrogen contained will pass through the catalytic converter. In this catalytic converter, carbon monoxide will be changed into carbon dioxide to reduce their toxicity, and then it will pass next for cryogenic distillation for separation between carbon dioxide and hydrogen gas, which can be proceed for CO2 and H2, which can be stored for future use and development. For our wastewater treatment method, we have proposed 4 methods, which is activated sludge, advanced oxidation process, air stripping process, and adsorption process to treat methanol from methanol water mixture, which is discharged from stream 23. After comparing 4 proposed methods, we have choose advanced oxidation process as our main method to treat methanol from methanol water mixture. Methanol can be degraded by advanced oxidation process by mixing methanol with a strong oxidizing agent such as hydrogen peroxide with the presence of UV light. This UV light will react with hydrogen peroxide to produce hydroxyl radical, and this hydroxyl radical will react with methanol to produce carbon dioxide and water as the last component in the methanol water mixture. The reason we choose advanced oxidation process is because it leaves no sludge after the treatment process, which reduce the sludge treatment cost. Besides, advanced oxidation process also require small area of operating, and advanced oxidation process also one of the fast reaction rate of degradation compound, and advanced oxidation process also do not introduce any new hazardous substance into the wastewater after the treatment in theoretically. There are two options in our alternative wastewater treatment method. The first is treat wastewater on site. Wastewater from stream 23 will going for primary wastewater treatment to remove suspended solid and particulate matter in the water. The production of sludge from primary clarifier will proceed for filter press process to remove water, which can reduce the sludge weight and also operating cost. The water that have been free from suspended solid will proceed for advanced oxidation process to remove methanol from the water. The water that have been free from methanol will proceed for hydrogen peroxide treatment to remove excess hydrogen peroxide by adsorption process using granular activated carbon. Another alternative is send wastewater directly to third-party prescribed premise by DOE, which is Quality Alam. Wastewater from stream 23 will be held in a short period in a storage tank before being collected by Quality Alam. All treatment process will be done by the Quality Alam.
This table shows the cost for the option 1 to treat our waste. This includes the equipment cost and the operating cost per year. As you can see, the equipment cost is pretty high, with the operating cost is also pretty high. This table shows the overall cost for the second option of our wastewater treatment. And as you can see, option 2 cost is much higher than option 1. And based on the cost of wastewater treatment, option 1 would be a much better selection since lower operating cost per year. Hence, build an on-site wastewater treatment plant being selected for this project.
Safety. General plant safety assessment for production of methanol and potential hazards. Methanol is highly flammable and toxic, which can cause permanent blindness, poisoning, and also possibly death due to the ingestion or inhalation of methanol. When handling with methanol, avoid direct exposure and also wear safety gear to protect body parts. We need proper ventilation when handling with the methanol. In methanol plant, we need also fire and explosion hazard since methanol is highly flammable. We must also make sure to call local fire department if methanol spill occurs and make sure to isolate the spill or leak area. Storage of methanol. When storing methanol, we must store it in closed system or approved container which can be used to store the methanol. We never leave the methanol in open air. We also make sure to label the container based on the regulation. Storage handling in place at all storage and transfer points is needed. There is also potential for public could be exposed to this chemical product through several exposure conditions include workplace exposure, environmental release, large release, or also consumer exposure where the consumer by the product itself. Plant layout. Utilities building is located near the process section to give most economical supply such as steam to the process unit and important in reducing of heat losses. This plant layout is developed to ensure the safety for the workers and also all assets in plant. The plant layout together with the emergency evacuation pathway should be affixed in various areas within the plant in order to allow systematic and smooth evacuation of workers during emergency events. This plan will be updated regularly as the plant layout may be altered due to the future expansion. This is our plant layout. Okay, now we go to the SF analysis and study. In this SF analysis, we conduct analysis based on our components we are used, which is reactors, distillation column, flash drums, and also other unit operations. Okay, for example, in reactor we can take example of cooling water, and in our cooling water our parameters is flow. Okay, the deviation is no flow. If there is no flow, what are the causes? Is cooling water service failure or pipe broken or clogged, controller failure or valve is closed. The possible consequences is temperature of inside reactor increase drastically or possible of process runaway. What are the action that we need to take is install cooling water flow or install filter with maintenance procedure, and also we also make sure to check and monitor cooling water regularly. There are also other study notes for the reactor, and also we also conduct other possible parameter in the reactor, which is temperature, and also we also have another study note which is reactor vessel, and its parameter is flow, and also it also has parameter of temperature and also pressure. These are the our SF analysis study for the cooling water and also reactor vessel in the reactor. Okay, now we move on to the flash drum. The process parameters for flash drum is flow. If there is no flow, the possible causes is pipeline leakage or block from inside, or controller failure or valve is closed. The consequences is separation can occur, pressure build-up in pipeline, loss of production. The action required is install flow controller and indicator and periodically inspect the system to ensure its integrity, install bypass string to the column, or install digital sensor to detect leakage. Here is the other deviations in the flash drum, and also other parameter we can be used in the flash drum is level, and also pressure and temperature. These are the SF analysis for the flash drum 1. Now the SF analysis for flash drum 2 is same as the flash drum 1. Okay, we move on to the distillation column. The study note for the distillation column is column vessel, reboiler and condenser. The process parameter is flow. For deviation, no flow. If possible causes is pipeline leakage or block inside, or controller failure or valve is closed. The possible consequences is no separation occur in the column, pressure build up in pipeline, or loss of production. The action required is install flow controller and indicator, periodically inspect the system to ensure its integrity, and also other solutions. Same as others, there are also other deviations for the flow in the distillation column, which is high flow, low flow, reverse flow, and for the temperature is high temperature and low temperature, and for the pressure is high pressure and low pressure. Okay, for the level we have high level and low level, and this is as an analysis for distillation column. Okay, now we move on to the heat exchanger. The study note for the heat exchanger is also same, and also the process parameters for heat exchanger, for example, is flow. Okay, deviation, no flow from cold process stream or no flow from hot process stream. The possible causes is pipeline leakage or block, or controller failure or valve is closed, and broken heat exchanger tubes or pipes. The possible consequences is pressure buildup in pipeline or pipeline rupture when cooling absent and hot process stream overheats, and also desired temperature cannot be achieved. The possible solutions or action required is install flow controller and indicator, and also make sure to conduct inspection periodically, and also install bypass stream to the column and install digital sensor to detect leakage. Okay, here is the other deviation is high flow and also low flow for the low flow parameter. Okay, here we got other parameter for the heat exchanger, which is temperature, which is the deviation is high temperature or low temperature. Okay, now we move on to the compressor. For the compressor, the process parameter is pressure. Okay, the deviation is high pressure or low pressure. As for the high pressure, the possible causes is control valve failure. The consequences is reactor will operate at high temperature, and also pipeline rupture due to the pressure buildup. The action required is install emergency shutdown or install pressure indicator and controller, and install high pressure alarm. Periodically inspect the system to ensure its integrity. As for the low pressure, possible causes is the less flow in the compressor, pipeline leakage. Possible consequences is affect reaction rate in the reactor because not the optimum pressure for the reaction. The action required is install emergency shutdown, install pressure indicator and controller, install low pressure alarm, and periodically inspect the system to ensure its integrity.
Profitability analysis. Profitability analysis of a project development is needed to be carried out as the main purpose of investing money in chemical plant to gain profit. First, the expenses of the materials are calculated by taking the price for the raw materials and the product, which is methanol, are multiplied by the feed mass flow rate. Then, by assuming that the plant is operated 7,920 hours for the whole year, the annual cost for raw materials and annual revenue to the plant is estimated. Next, the term utilities include cooling and heating utilities, steam and electricity. The current cost of utilities supplied by the utilities company can be obtained from local area offices. Followed by that is the total production and manufacturing cost summary. Total production costs include general expenses and manufacturing cost. Manufacturing cost comprises of direct and indirect production costs. At the end of the summary, the rate of return calculated by obtaining the value annual profit after income taxes and depreciation value. The return of investment or rate of return obtained is 86%. Next, cash flow series is used to determine the payback period, discounted payback period, and net present value of methanol production plant. plant life for chemicals is 20 years. Therefore, the total operating period of methanol plant is assumed 20 years, excluding the 3 years for the plant construction, with a total capital investment of 960,233,471.02 ringgit. For the first year, it is assumed that 80% of the sales income being achieved because this is a new plant. Assumptions were made where for first year 10% of total capital investment is loaned by bank, for second year 25% of total capital investment is loaned by bank, and for third year 65% of total capital investment is loaned by bank. The cash flow of undiscounted rate must be calculated first to determine the period of time after startup until cumulative undiscounted cash flow gained back the fixed capital investment. This table shows the cash flow analysis for without a discount rate where the interest rate equals to 0%. This table shows the cash flow analysis with discount rate which varies from 40, 60, 80 and 87.01%. For the undiscounted cash flow analysis, where the interest rate equals to 0%, the payback period is 0.71 operating years after 3 years of startup period. This means that the plant will start earning after 0.71 year or 3.71 year in total, which is less than 5 years. For the discounted cash flow analysis, payback period varies accordingly. It can be seen that the payback period is 1.54 year, 2.15 years, 3.91 years for 40%, 60% and 80% of discount rate respectively. Within the period of 20 operating years after the start up in year 3, the net present value equals to 0 if interest rate equals to 87.01%. 87.01% is the internal rate of return, which is known as the maximum allowable performance discount or decline rate.